Hello, this is A. Srinivas, Lecturer in Physics, Vignan Junior College. Hi students, good morning one and all. Welcome to Vignan Digital Classes. We have been discussing ray optics chapter. We completed 3 videos belongs to ray optics. Today we continue the phenomena of ray optics, and especially today in this session we confine to the total internal reflection. Total internal reflection is the very good phenomena which is useful in our daily life in so many applications. Here we would like to know about the definition of total internal reflection and applications of total internal reflection, and numericals belongs to total internal reflection. Here you are observing the diamond. We know the glorious glitterance exists for the diamond. This glorious glitterance of the diamond is due to the phenomena of total internal reflection. Nowadays we are using a lot of information through internet. So there is a communication in form of radio waves from one continent to another continent, from one place to another place. The exchange of this information in form of radio waves now at so vast and fast is by the virtue of the optical fibers. In this animation you are observing the optical fibers through which radio waves are communicating nowadays. And to know the interesting reasons behind the glorious, fabulous glittering of the diamond and way of communication through optical fibers, so all those things. Similarly, there are mirages formed in very hot days in highways as well as in deserts. The secret behind the formation of mirage, all these wonders which are happening around us will be answered with the help of this total internal reflection phenomena. So let us move on to the contents of total internal reflection. So first we define the total internal reflection, the definition of total internal reflection, expression for total internal reflection, equation form. Then application. We go to applications of total internal reflection. First one is optical fiber. So it is a wire made up of quartz glass. So the special construction of optical fiber used to carry the information and very much useful for communication. Even in medicine we use the optical fiber, and this is one animated example of the optical fiber. And next the total reflecting prism. Sometimes when the light is incident at proper angle of incidence on the prism reflect the incident light on it. So prism may behave as a total internal reflecting surface. So the total reflecting prism will be discussed. Next one is the sparkling of diamond. Here we are observing the diamonds. We know that they are too much cost because of this sparkling nature, and we have to discuss about what is the reason behind this sparkling character of the diamond. Next we go to the next application, formation of mirages. So as I explained, in hot summer days, in hot seasons, and even on highway, we undergo an optical illusion of presence of water. There would be no water, but we undergo optical illusion of presence of water at farthest distances from us, especially during hot days. The reason behind the optical illusion will be discussed in the mirage formation. And the numericals belongs to this total internal reflection and optical fibers. So let us move on to the very important definition. After that we go for each and every application. Let us move on to the definition. First of all, here we have the total internal reflection. Let me define the total internal reflection. A total internal reflection is the phenomena of complete reflection of light. Here the phenomena of complete reflection of light. So even the title itself we have the reflection. So the phenomenon of complete reflection of light back into the same medium for angles of incidence greater than the critical angle of that medium. So each and every medium has its own critical angle. If any light is incident or traveling from denser to rarer at an angle of incidence greater than the critical angle, it may reflect it back totally into the same medium. This phenomenon is known as total internal reflection. Here we have two new terms. First one, the one is angle of incidence, and for any angle of incidence greater than any angle greater than the critical angle is one more thing. So if bodies are incidenting at angles greater than critical angle, the light may come back into the same medium. Here we have to discuss what is the critical angle, and then for greater than critical angle how the light is come back into the same medium. So we have to know two things: what is meant by critical angle. For any angle of incidence greater than critical angle, why light is come back into the same medium. Then we may know about the complete idea about the total internal reflection. So let us have a diagram to know about these definitions. So let this be a denser medium. Students, on the screen you are observing a denser medium, relatively more refractive index medium than the surroundings. Hence it is a denser medium. Here this blue color, this violet color, this is the denser medium especially. Students, you are observing this violet color one is the denser medium and grey color one is the rarer medium. Let us have two mediums separating each other, denser and rarer. Okay. Here the grey color which is at the top is the rarer medium, let it be A, having refractive index mu A. The violet color is the denser medium, let it be made up of glass, any denser medium, let it be glass having mu Z. Here this is the object from which light rays are emerging. So here this is the first light ray. Look into the animation carefully. Here I am showing one after another. This is the object from which light rays are emanating. So this is the emergent light ray from the object, and this first light ray is incidenting and travelling along the normal. So angle of incidence is 0, angle of refraction is also equal to 0. While light ray is travelling from this lower denser to the top rarer medium, it undergoes the phenomenon of refraction. But here the light ray is incident at an angle of incidence 0, hence it has the angle of refraction also equal to 0 degrees. Therefore it moves without any deviation. This is the first case in which we consider the light ray. Let us increase the angle of incidence in different steps. Let us consider the second ray. See the animation carefully. Here this is the second ray. Here this is the normal drawn to the interface. Therefore this incident light ray, this is incident light ray at an angle of incidence greater than 0. Then some part of light may reflected back and some part of light is refracted into the second medium. Once again, this is the incident ray from the object, incident at the interface, and some part of light is refracted into the second medium, some part may come back reflected in the same medium. But this is not the total internal reflection, this is the partial reflection. Most of the light get refracted into the second medium. Okay, let us increase the angle of incidence. Here, suppose you have I1 angle of incidence. Here at this angle of incidence is 0. Now this is I1 angle of incidence and this is I2 angle of incidence. Observe it. We are gradually increasing the angle of incidence step by step. In the third case, we further increased the angle of incidence made with normal. So according to Snell's law, angle of refraction also increases. One thing you must observe: light rays traveling from denser medium to rarer medium. Students, this is the very important point. Light ray is traveling from denser medium to the rarer medium. Then light ray move away from normal in rarer medium. So you are observing same thing. Light ray is moving away from normal. As we increases the angle of incidence in case to case, step by step, angle of refraction also get increases. So refracted light ray moves away from normal and come close to the interface. That's what we are observing. As we are increasing angle of incidence, angle of refraction is get increasing and refracted light ray get come close to the interface. Let us consider one more case in which we further increases the angle of incidence. So this is the normal. Here at this, especially at this angle of incidence, the refracted light ray has angle of refraction 90 degrees. This is the very important point. For this peculiar light ray of a certain angle of incidence in denser medium, the refracting angle in rarer medium exactly becomes 90 degrees, so that no more light in the rarer medium, the refracted light ray passes along the interface. Let us observe the values. This angle of incidence is IC. Angle of incidence is IC, known as the critical angle, for which angle of refraction is 90. So this is we get answer for this second part. What is meant by critical angle? Here we use the term critical angle. Critical angle is the angle of incidence in the denser medium, for which the angle of refraction in rarer medium is 90 degrees. So that the refracting angle is 90, the refracted ray grazes along the boundary surface. You are observing it is travelling along the interface, grazes along the boundary surface. R is 90. So angle of incidence in denser medium, for which the refracting angle becomes 90 degrees, is the critical angle. Hence this is the definition. Now further improve the incident angle, increases the refracting angle. So this is the case. Here we increases the angle I greater than IC. Let this be the angle which is incident angle is greater than critical angle. I greater than critical angle means refracting angle more than 90. Refracting angle is more than 90. Then definitely the refracted ray passes or come back into the denser medium. For refracting angle more than 90, this is the refracted ray having angle of refraction more than 90, so that it come back into the same denser medium. Hence it is showing the phenomena of reflection. There is no more light in the rarer medium, whereas we have light in the rarer medium for the previous cases, especially while light is travelling from denser to rarer medium and incident at the interface at an angle exactly, for any angle greater than critical angle, refracting angle is more than 90 degrees, so light ray must come back into the same medium. This phenomenon is known as total internal reflection. That's what we are observing. Here, let us see the definition once again and observe the statement according to the diagram. Total internal reflection is the phenomenon of complete reflection of light back into the same medium. So here, this is the case in which we are observing a complete reflection of light back into the same medium. In this, for this case, in which angle of incidence in the denser medium is greater than critical angle, the total light come back into the same medium. So phenomena of complete reflection of light come back into the same medium. For angle of incidence greater than critical angle of the medium, this medium has certain critical angle. For incident angle greater than critical angle, light come back into the same medium and totally it come back into the same medium. This phenomenon is known as total internal reflection. Let us see the conditions to have this total internal reflection. First one, the incident ray must be in optically denser medium. Here the light rays are coming from O. This object must be in denser medium. Then only refracting angle in rarer medium is moving away from normal and it may reach a condition of greater than 90. To have refracting angle in rarer medium greater than 90, the light ray must move away from the normal. This is possible when light rays are incidenting in denser medium. So this is the very important condition. You must remember this one forever. The incident angle must be greater than critical angle and that incident ray should be in denser medium. The incident ray must be travelled in the denser medium and the angle of incidence in the denser medium must be greater than critical angle. So two very necessary conditions to observe the phenomena of total internal reflection. As explained here, for this ray we are observing total internal reflection. So that to have the phenomena of total internal reflection, light ray must travel from the denser medium. That is the first condition. Second one, the angle of incidence must be greater than the critical angle. So these two are the very must and should conditions to observe the phenomena of total internal reflection. So let me to derive the expression for the relation of critical angle and refractive index of the denser medium. So let us move on to the derivation. Relation between critical angle and refractive index. So critical angle, already we defined it. That is the angle in the denser medium for which refracting angle is 90. So that light ray grazes along the boundary, that is critical angle. We would like to know the relation between critical angle and refractive index. So let us consider the definition once again. Critical angle is the angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degrees. According to a clear explanation a few seconds back, critical angle is the incident angle in denser medium for which angle of refraction is greater than 90 degrees in rarer medium. So in this animation also you are observing how the refracting angle is changing with changing the angle of incidence. That the lower one is the denser medium, yellow color, white one is the rarer medium. I am showing all the cases in this animation. You may observe here the angle of incidence increases. At this angle light ray grazes. So now observe it. At a particular angle light ray grazes. This is critical angle. More than that it come back into the same medium. Especially particularly for this condition you are observing the critical angle when you look into the animation. At a particular place in which angle of incidence is critical angle, the refracted ray grazes along the surface. So let us have the derivation for it. So apply Snell's law at this boundary, that is refractive index of second medium with respect to first medium, mu Az. Refractive index of second medium is, let it be A, first medium is glass. For example, we are considering rarer medium as air and denser medium from which light is incident is glass. Therefore mu2 by mu1 is the general formula. The refractive index of second medium with respect to first medium is sin I by sin R. For critical angle I is equal to IC, R is equal to 90, angle of refraction is 90, sin 91, so sin IC. So hence we get the formula sin IC is equal to refractive index of air with respect to glass. So we write, here we comes to an idea, that is if IC is the critical angle, sin IC is equal to refractive index of rarer medium with respect to refractive index of denser medium. Hence this is the very important formula regarding this critical angle. If so, IC is the critical angle for which refracting angle is 90, then sin IC is equal to refractive index of rarer medium by denser medium. Affords refractive index of air by glass for this example, especially. For any rarer medium, mu rarer and mu denser. For example, rarer medium is air and denser medium is glass, mu A by mu Z. We know that air may have refractive index of 1. For air refractive index is 1. Hence mu A is 1 by mu Z is mu. 1 by mu, that is mu denser. In that way we write the expression for sin C, especially for the example of air medium as rarer and glass medium as denser medium. Therefore we represent the same thing. Sin IC is equal to 1 by refractive index of glass with respect to air. If you take the reciprocal of this one, so mu A by mu Z also equal to 1 by mu ZA, we write the same thing. You remember, this is the important formula. Sin IC is equal to refractive index of rarer medium by denser medium. A light ray is allowed to incident from denser medium travelling into the rarer medium. Critical angle is the angle of incidence in denser medium for which refracting angle is 90. Then sin IC is equal to refractive index of rarer by refractive index of denser. If rarer medium is air and denser medium is glass, mu A by mu Z. Assume rarer medium air is of 1 value, so 1 by mu Z. So this is the crucial formula. And we know that the refractive index and wavelength are inversely proportional. Sin IC is equal to, we write mu A divided by mu Z. Observe it, mu A divided by mu Z. And wavelength and refractive index are inversely proportional, so lambda Z by lambda A. Sin IC is also equal to, wavelength and refractive index are inversely proportional quantities, related quantities. So sin IC is equal to mu A by mu Z, also equal to lambda Z divided by lambda A. as mu and lambda are inversely proportional to each other. So here one important thing which is useful for objective examinations. We know that red color has maximum value of critical angle and violet color has minimum value of critical angle. What is the reason behind it? So as far as wavelength is concerned, the wavelength is more for red color. We know that red is of greatest wavelength visible light. So lambda is high, therefore sine of critical angle is inversely proportional to refractive index and directly proportional to wavelength. Sine of IC inversely proportional to refractive index of denser medium. Refractive index is inversely proportional to wavelength. As red color has more wavelength, it has more critical angle. Among visible lights, violet has less wavelength. We know that least wavelength of visible light is violet. Violet has less wavelength, hence less critical angle. Hence this is the condition. Statement: red color has maximum value of critical angle because of maximum wavelength, and violet color has minimum value of critical angle because of less wavelength. This is about the critical angle, how it is varying with color. So we represent it. Now let's move on to the very important area, that is applications of the reflecting, total internal reflection. Applications of total internal reflection. Let us see what are the possible applications. One is optical fiber. Second one is total reflecting prism. Third one is sparkling of diamond. Fourth one is mirage formation. These are the four important applications of total internal reflection that we observe in our daily life also. Optical fibers, nowadays they are useful very much for the communication of radio waves from one place to another place in vast and fast conditions. So a versatile device, optical fiber is a versatile device which is very much useful for the communication nowadays. And total reflecting prism, sometimes at a particular conditions, prism behaves like a total reflecting medium and it reflects the incident light backwards. And sparkling of diamond, in the animation you are observing the diamond, the sparkling of diamond is also a consequence of total internal reflection. And during hot days on highways as well as in deserts, we are observing formation of mirages. We have to know the reasons behind them by applying total internal reflection. We will discuss one by one. So let us move on to the first case of optical fiber. This is a very interesting one and it has very good number of applications in our day-to-day life. So optical fiber, nowadays optical fibers are extensively used for transmitting audio and video signals. This is important point. You must recognize it. Nowadays optical fibers are extensively used for transmitting audio and video. Of course, we change the audio and video signals by using a transmission phenomena. We convert any audio and video signals to the radio waves in form of transmission. That radio waves are in form of digital signals. They are very much transmitted from one point to another point, one place to another place, one country to another country, one continent to another continent, either a small separation or a large separation. They are simply transmitted from one point to another point by the optical fiber. So nowadays optical fibers are extensively used for transmitting audio and video signals, of course by transforming them into electromagnetic wave to long distances. Optical fibers to make use for the phenomena of total internal reflection. So optical fibers to uses the phenomena of total internal reflection. This is the present explanation. So the optical fibers uses the phenomena of total internal reflection and transmit audio and video signals through large distances. Optical fibers are fabricated with highly quality composite glass and quartz. So material in the preparation of optical fibers is the highlighted point. Glass and quartz. Glass and quartz are very much useful to prepare an optical fiber wires. Each fiber consisting of a core and cladding. The main two parts of the optical fiber is a coaxially constructed core and cladding. The inner one is the core, surrounded one is the cladding. Core and cladding are the two important materials of the optical fiber. The refractive index of material of the core is higher than that of the cladding. This is the very crucial point, because to have phenomena of total internal reflection, light ray must travel from denser medium to rarer medium. To achieve this condition of total internal reflection, the core must be higher. Refractive index of core is higher than the cladding. Cladding is the surrounding medium that must have less refractive index. Core is the axis medium at which high refracting medium is kept. Anyhow, the inner core and outer cladding are made up of a composite glass and quartz. At suitable conditions, it shows the phenomena of total internal reflection. Let us see a schematic animated diagram of total internal reflecting optical fiber. This is a schematic diagram of optical fiber. In this animation, students, you may observe the optical fiber. The green color, which is at the center, along the axis of the optical fiber, we have the core. The core material of the optical fiber represented by green color one, and violet color surrounding material around the core is named as the cladding. Core is the centrally adjusted material, surrounding material is known as the cladding. This yellow color one is the light propagating along the core of the optical fiber due to the phenomenon of total internal reflection. So from the air medium we incident the light into the core of the optical fiber. From air medium we launch a light or we incident a light into the core of the optical fiber. Because of the suitable launching angle at the interface of the air and the core, so at this phase, this is the normal drawn here, at this point the angle of incidence is greater than the critical angle. Here let this be the normal drawn. This is the angle of incidence. This must be greater than the critical angle, so that light incidenting at the core and cladding interface, for which the angle of incidence is greater than the critical angle for the given pair of surfaces. So for the given pair of this core and cladding surfaces, there is some critical angle. According to the formula, sin IC is equal to refractive index of the rarer by refractive index of cladding. We have this formula, sin IC is equal to, when IC is the critical angle, I suffix C is the refractive index of rarer by refractive index of denser. Rarer medium is the cladding here, so refractive index of cladding material by refractive index of core material is IC. We calculate the IC value with this formula for the given pair of core and cladding surfaces. If the incident angle, we launch the light ray from air medium to incident the interface at an angle greater than critical angle, so that it must go the phenomena of total internal reflection. So continuously the light ray undergoes the total internal reflection phenomena for each incident at the interface of core and cladding, and it moves continuously forever and ever until the material ends. So this process is very much useful in the propagation of any type of electromagnetic wave, a visible light or radio waves. So most of the waves that are useful for transmission is radio waves. They are transmitting this audio and video signals first transfer to electromagnetic waves by using a transmission phenomena. That electromagnetic digital signals are allowed to transmit through the core of the optical fiber by using the phenomena of total internal reflection. This is a very easy way of communication. So without any interference with other signals, without any disturbance, there are three advantages of using optical fiber. This light ray cannot be interacted with any other light rays. There is no interference between the electromagnetic wave in optical fiber, and there is no noise signals are added to them. There is no distortion or disturbance to the pure signal because it is not interacting with any other signals. So without any disturbance it can travel. One more important one is there is no loss of energy because there is no refraction to the other medium. Only the light which is sent into this optical fiber undergoes total internal reflection. That means total light is come back into the same medium without loss of energy. That's why without loss of energy, and moreover it travels with the velocity of light. Any sound and video signals transfer to electromagnetic signals. All electromagnetic signals travels with a speed equal to that of light. So it is a vast communication. It is a very fast communication. And without any interference, distortion, disturbances, we send any number of signals at same time. We can any number of signals through one single optical fiber through one place to another place, which are separated a large distance in very minimum time. So this is one advantage of optical fiber. Nowadays we are using them for so many purposes. So let me to derive the expression for numerical aperture of optical fiber. Especially this is the derivation part for JEE main examination. For objective examination, I would like to do this derivation. Numerical aperture of optical fiber. So let us consider the optical fiber in which the inner one is the core. We know that inner one is the core and outer one is the cladding. So I am representing, this is core. The inner one, this one is the core. Students, this one is the core. Don't get confused. If you consider the core as a cylindrical object along the axis, so it is made up of a composite glass and quartz. The inner one is the core and in form of a cylindrical shape having a refractive index N1. This is a denser medium. Core must be a denser medium having refractive index N1 surrounded by a less refractive index medium. Cladding is the medium surrounding the core having less refractive index N2. Clearly, we must have the relation such that N1 must be greater than N2. Then only the phenomena of total internal reflection will happen between the interface of the core and cladding. The inner one must have more refractive index than the outer one. Core must have the more refractive index than the cladding. Here, the light, which light is to be transmitted through large distances through the optical fiber, that must be launched here. This is the launching light. Here you are observing the launching light at an angle alpha. Alpha is the angle of launching. Maximum angle at which a light must be launched or sent into the core from air. This is the air medium. Let medium be refractive index N. Of course, N in most of the cases we consider N is equal to 1, air medium. Let this be the medium from which we are launching a light ray into the optical fiber. This construction of core and cladding is optical fiber, and from the surrounding, most probably air medium, we are sending or launching a light ray into the core cladding medium. So let the outside medium of this optical fiber having refractive index N, most of the cases let it be 1. Now the light ray is launched into it at an angle of incidence alpha. Then as light ray is traveling from rarer to denser, core is always a denser medium, then light ray move away from normal. This is the normal. Here in case of light ray traveling from rarer to denser, this is the normal. Observe it. This is the normal line. I am showing once again. So when light ray is traveling from outside air medium to the core medium as the denser, light ray bends towards the normal. Let this theta be the angle made with the normal of the air core interface. Normal line to the air core interface. So it bends towards the normal. And this refracted ray incident at this interface of core and cladding. This is what we discussed so far. So far we discussed this form of internal reflection. This is the core and surrounding one is cladding. At this interface light ray is incident. This must be greater than critical angle, at least critical angle. If this angle of incident is greater than critical angle, then we observe the phenomena of total internal reflection. So this is the explanation. Let us go to the derivation part. So here when we apply the Snell's law at this interface of light ray traveling from outside medium to the core medium. First we launch a light ray from outside medium to the core medium having refractive index N for outside and N1 for core medium. Then product of refractive index and sine of angle of incidence is constant. So for outside medium n sin alpha, for core medium n1 sin theta. So this is the one form of Snell's law, that is product of refractive index and sine of angle of either incidence or refraction is constant. So for outside medium n sin alpha, for core medium n1 sin theta, theta is the angle of refraction. These two are equal. And next one, we convert theta to critical angle. We need a relation between the critical angle and this launching angle. So from this right angle triangle, we change the critical angle is equal to 90 minus theta from this right angle triangle. So critical angle is 90 minus theta, or theta is equal to 90 minus critical angle. So n sin alpha is equal to, this theta is equal to 90 minus theta c. So n sin alpha is equal to n1 sin 90 minus theta c. We know that sine of 90 minus theta is equal to cos theta. So n sin alpha, alpha is the launching angle. N1 cos theta c is the critical angle to start the total internal reflection. Then we write sin alpha is equal to n1 by n into cos theta c. Remember, alpha is the launching angle, n1 is the refractive index of the core, n is the refractive index of the surrounding medium. This is the medium from which light is launched, outside medium, and theta c is the critical angle. And we would like to represent this launching angle in terms of core cladding refractive indexes. We need the formula of launching angle in terms of core and cladding refractive indexes, mu1 and mu2. For that we have to eliminate cos theta c. That is, theta c is the critical angle. To eliminate the cos theta c, we use the concept of critical angle expression. So we know that, of course, cos theta c is square root of 1 minus sin square theta c according to trigonometry. Next one, apply the Snell's law at the interface at which there is a phenomenon of total internal reflection. Light ray is traveling from core to cladding at this point B, and light ray incident at point B at the interface of core and cladding. Then applying Snell's law, we get n1 sin theta, here theta c is the incident angle, n1 is the refractive index, n1 sin theta c for outside cladding medium, n2 sin 90. Here we are assuming a limiting condition which refracting angle is 90 degrees, n2 sin 90. Therefore n1 sin theta c is equal to n2, therefore sin theta c is equal to n2 by n1. So replace sin theta c in this formula. So that is by this value, therefore we get cos theta c is equal to 1 minus sin square theta c, replace theta c by n2 by n1. So 1 minus n2 by n1 whole square. And substitute this cos theta c in this formula to get launching angle relation. Sin alpha is equal to n1 by n into square root of 1 minus cos theta c value, n2 by n1 whole square. Take LCM, so that it is n1 square minus n2 square by n1 square. So take LCM, n1 square minus n2 square by n1 square. Root n1 square means n1 in denominator, n1 in numerator get cancelled. So we get, that is square root of n1 square minus n2 square divided by, take n into the square root, that is n square. Square root of n1 square minus n2 square divided by n square. n1 is the refractive index of core, n2 refractive index of surrounding cladding, n is the outside medium refractive index. Then sin alpha is equal to square root of n1 square minus n2 square divided by n square. But practical cases, the n is equal to 1. Already we write it. For outside medium, let it be air medium of refractive index 1. Then replace denominator by 1, then sin alpha is square root of n1 square minus n2 square. From this we find sin alpha, the expression we find alpha. Alpha is known as the launching angle to have the critical angle. Then numerical aperture is square root of n1 square minus n2 square. For given pair of core and cladding, for given pair of this core and cladding have a refractive index n1 and n2, the launching angle alpha is calculated by this formula. Sin alpha is equal to square root of n1 square minus n2 square, or numerical aperture Here this is the maximum possible angle at which light ray may be incident. So in form of a cone, in all directions from the cone at end side. So you may launch the incident light ray at an angle less than this value. Hence this is known as the numerical aperture. This diameter is the numerical aperture of the incident light ray. Any light ray below this surface of the cone may undergo total internal reflection in core and cladding interface. So to have a total internal reflection, there is a condition of launching angle. So for any angle less than that alpha, we get total internal reflection, and this diameter is considered to be numerical aperture. This diameter calculated by using sin alpha, opposite side by hypotenuse. By using sin alpha we calculate diameter, hence it is known as numerical aperture of the given pair of core and cladding, that is square root of n1 square minus n2 square. So let us move on to the applications of the optical fiber. So far I completed the launching angle phenomena. So applications of optical fibers. In applications of optical fiber, so we use the optical fiber very well for communication purpose. Nowadays we are transmitting the digital signals. Video audio signals are transformed to electromagnetic wave in form of digital signals. They are simply transmitted to large distances in very short time through optical fibers. So in this animation you are observing the light rays traveling in optical fibers. This is the one way, and here this is the light coming from the optical fibers. This is the decoration light in houses. We can use the decoration light. This is the source of light, and this is sent into the optical fiber. Through this optical fiber the light is transmitted. At this point we are observing the light emitted from the comes out from the optical fibers. So throughout this optical fiber the light is traveled from the source, and at the end of the optical fiber it emerges out from the optical fibers. It appears very beautiful. In showcases as a decoration lamps, we can use the optical fiber equipped lamps through which light is transmitted. At the tip of the optical fiber it emerges, the light passes through it. It appears to be a wonderful and a beautiful decorating lamp. So next one, to move on to the further applications of the optical fiber, let us discuss one numerical problem, very important model. Find the critical angle. Already we discussed the critical angle expression. So let us see one example, a numerical example to find out the critical angle. Here find the critical angle for the diamond. So diamond is the very important object. Here we have to discuss the applications of the total internal reflection, that we observe the glitterance of the diamond. To know the glitterance of diamond, let us consider the object, that is diamond. Diamond air boundary, we have to find the critical angle for the diamond air boundary. Refractive index of diamond. So students, remember, refractive index of diamond is very high compared to ordinary objects. For water, refractive index is most probably 4/3, 1.33. For most of the glasses, refractive index is 1.5. Of course, it varies from glass to glass. We have different types of glasses made up of different materials. So in an average, we consider the refractive index of glass as 1.5 compared to ordinary glasses that we use as the windows in our daily life, or tabletop glasses, or every time windows of the cars, vehicles, we use the glass. Generally those glasses may have refractive index around 1.5. Whereas the diamond, which is used as the decorating item, diamond is the two-cost material, we know it. It's if you take the diamond in large amount, it is in the order of crores of rupees. So two-cost material, the ordinary and common people can't buy the diamond because of its cost. So refractive index of the diamond is 2.42, too much high. Whereas refractive index of glass is just 1.5. It is around one number more than the refractive index of glass. This is the greatness of the diamond. Diamond has its greatness because of its refractive index, too high compared to ordinary glasses. So if refractive index of the diamond is 2.42, diamond air intercore, then what is its critical angle? We know that the critical angle is C, then sin C is equal to 1 by mu for a denser air boundary surface. If mu is the refractive index of denser medium, especially diamond medium, then simple equation is sin C is equal to 1 by mu. That is equal to 1 by 2.42 sin C. From this we calculate C is equal to 24.4 degrees. This is the least critical angle given by the diamond compared to ordinary glasses. As refractive index goes on increasing, critical angle goes on decreasing. Now what is the difference between ordinary glasses? Ordinary glasses are not too cost. They are available at each and every place. But especially the glasses are useful every time. We can produce number of glasses. But rarely we use the diamond. They are too cost material. What is the difference between the glass and the diamond? Only difference is refractive index is so high so that critical angle is so low. The critical angle of the ordinary glass is around 40 degrees because of its less refractive index, 40 degrees. Whereas the refractive index is high for diamond, so that critical angle is very low, 24.4 degrees is the critical angle of the diamond, which is less than the critical angle of glass, ordinary glass. That is the difference between glass and the diamond in mu point of view and critical angle point of view. So let us move on to the application. See, a sparkling of diamond, glitterance of diamond. So as I explained, diamond is a material, of course appears to be in form of a glass, but a transparent medium. Though it is a transparent medium, but its refractive index is refractive index of diamond is 2.42, so that critical angle is very low, 24.4 degrees. We solve it already in numericals. Because of the less critical angle, it has less critical angle of its nature, and moreover there are so many cut parallel planes, cut surfaces on the diamond. Cutting of diamond is a very critical thing in formation of diamond. The greatness of the diamond, the sparkling of the diamond depends upon the refractive index of the nature of the diamond. That is the one thing. Second one is preparation of diamond, cutting of diamond. Diamond is cut into different planes in a proper way, so that if any light enter into the diamond, so diamond doesn't have any light. The outside sources, as sunlight or any light in the room, we have a lot of light in our room, and we stands any place we have light coming from the sun. Any ordinary sunlight or light once enter into the diamond, then it undergoes multiple reflections, multiple total internal reflection. This is the crucial word. The light that enters into the diamond undergoes multiple total internal reflection for multiple number of times because of the less critical angle. Less critical angle and cutting of the diamond planes make the light to undergoes multiple internal reflection, so that that gives the sparkling to the diamond. So let us move on to the one more application, total reflecting prism. Here this is the animation or image in which you are observing, and this is the diamond, this is the prism, students. This is the surface of the prism. So let this be a prism. This is the incident light ray traveling along the normal. So angle of incidence is 0, angle of refraction is 0. So the incident light ray at this interface moves without any deviation. Incident at the inclined plane. At this inclined plane, this is one more surface of the prism. This angle of incidence is greater than critical angle, and the incident light ray at this interface moves without any deviation, and incident at the second plane, inclined plane surface, at an angle of incidence greater than critical angle, so it reflected into the back into the same medium at same angle of reflection according to laws of reflection. So this light ray traveled along this direction. Like this, this is a reflection. This is reflection takes place at this interface. Let us consider one more case. Here we are observing this blue and red colors. The blue color light at this interface are incident at an angle of incidence greater than this I is equal to 0, especially here. Therefore R, it travels along the normal, therefore R is equal to 0. It moves without any deviation. At this interface, this is the normal. Here angle of incidence is greater than critical angle of the given glass prism. So at same angle of reflection, it undergoes the reflection and travels along this line. Once again, this is the normal drawn. to the second inclined plane surface of the prism. Here this angle is also greater than critical angle. This is I greater than C. It undergoes total internal reflection at the same angle. It come back. So for this situation, it behaves like a mirror. So totally reflecting prism. Observe the title and observe this diagram. The same thing happened. And this is 0 degrees incident angle. This is more than critical angle. This is more than critical angle. By virtue of all these things, the light ray which is incident on the prism may come back. So sometimes without any loss of energy, the advantages of this reflection, there is no loss of energy. Without loss of energy, for this condition, the light ray reflected back. So sometimes the prisms may use the phenomena of reflection for the reflecting. So here we are changing the path of light ray by 90 degrees. Here we are changing the path of light ray by 180 degrees. Moreover, without any loss of energy, by using the phenomena of total internal reflection. So let us move on to the one more interesting application, that is formation of mirages. See, in this image, in this video, students look into it carefully. You are observing a mirage. This is the highway on which some passengers are walking along the highway. Some persons are walking along the highway. We are observing them at farthest distance from them. Our observation point of view is very farthest from them. At large distance we are observing them on the highway, and we are observing a pool of water here. In this image you may observe some pool of water in which a shadow of this moving persons. It shows some shadows of moving persons here. Look into the location at which I am showing. So at this place we are observing shadow of moving persons. Actually it is not possible for any person to walk on the water. We are not God. We doesn't have superpowers. We didn't walk. We doesn't walk on surface of water. But there appears to be walking on the surface of water. It is not at all possible if really water is there. But this is not real presence of water. This is optical illusion. Due to optical illusion, we assume that there is presence of water on the road and a pool of water on the road, and we are observing some image. This is totally optical illusion. Actually, there would be no water there, and we are assuming there is water. This is optical illusion. So optical illusion in which we assume some presence of water in hot days on highways or in deserts during hot conditions. The assumption of or a optical illusion, undergoing optical illusion of presence of water is known as the mirage. Here in deserts and as well as on highways, when you observe the farthest points, on hot days we undergo that optical illusion of presence of water, and this is known as the mirage. Let us move on to the formation of mirage. Formation of mirage. Here to have the that interesting thing, in previous session, previous part, I shown a video. So you might have observed it clearly. I explained it for a lot of time. Actually, persons are not walking on the water, but there appears to be walking on the water. This is the video taken in the mirage. This is the video of a mirage in which the persons are appears to be walking on water. So we are undergoing the optical illusion of presence of water. This is the mirage. How it is forming. So we are going to a scientific explanation of formation of mirages. Let us consider this is a desert or highway on hot days. Let it be a desert. Let this be a desert in which there is a plant. This is the plant or on the desert. Here this is the observer. We are here. We are observing a plant in the desert, or we are observing either plant or a tree, whatever it may be. Nothing different. We are observing a plant or a tree in the desert during very hot day. Desert means generally it is at high temperature. We are observing from here. We are observing a farthest kept plant or presence, plant or a tree on hot days in deserts. So actually this is the object from which light rays are coming, and what will happen to the light ray, and why we are undergoing optical illusion, why there is a pool of water, we are undergoing optical illusion of presence of pool of water, why we are observing an image of the tree here. So these things to be realized here. Here let us consider, this is the hot season region, hot region. Let this be the sand. This is sand, students. Let us assume this is sand, hot sand, very high temperature sand in summer season in desert. And this region is so hot air. Above the hot sand we have hot air. Let us look into this title. This is hot air. When you go to the higher levels, there is a cool air. So when hot air rises to the higher levels, it may cool down. So this is the cool air. Refractive index is also a function of temperature. Refractive index decreases with increase in temperature. Refractive index decreases with increase in temperature. So here temperature is hot, so high. So this medium is a rarer medium. This is the important point to know about the formation of mirage. The medium or air medium which is just above the sand, close to the sand at lower levels is the hot medium. Temperature is high. More temperature gives less refractive index. Hence this is the rarer medium. When you move to the higher levels, it is the cool air. Temperature gradient is such a way that temperature goes on decreasing with increasing heights. So there is a temperature gradient in the medium. With increasing height, temperature goes on decreasing. Hence the higher levels of the medium is cool air. As temperature decreases, refractive index increases. Hence this is the denser medium. We are observing actually a tree in front of us which is far away from us in a desert. So light rays are coming from the tree along this direction. But while light rays are traveling from denser medium to rarer medium, top one is the denser, bottom one is the rarer. This is the angle of incidence. When light ray travel from denser to rarer, so when you move down, we are going relatively rarer mediums. So when you are moving from top to bottom, we are moving into the rarer mediums. So this is the angle of incidence. This angle of refraction greater than angle of incidence, because our light ray is traveling. Light ray is not traveling in single medium in deserts. The medium is divided into gradients, so that the top one is the higher refractive index, bottom one is the lower refractive index. Refractive index goes on decreasing from top to bottom. So light ray is traveling from denser to rarer, so that refracting angle is more than critical angle. It bends away from normal, so that light ray, actually this is the light ray, it moves away from normal. Further, when you comes to this one, the light ray further more away from normal. This process is going on. At this point, the angle of incidence is greater than critical angle. At this, the incident angle, suppose if you consider this one, light ray is incident like this, the angle of incidence is greater than critical angle. Especially at this region, angle of incidence is greater than critical angle. So it undergoes total internal reflection. Light ray come back into the same denser medium. That's what so far we discussed. So this is total internal reflection taking place at this spot of critical angle, incidence angle more than critical angle. Light ray come back to the same medium, and light ray bends like this, and we observe the light ray. So now light ray enters into our eye along this path. So then we undergo that light would be coming from this point. Light would be come from this point. So we undergo optical illusion that this position of the tree is here. Because of light is not falling from tree to our eye directly, light enters into the eye along this direction. So opposite to that, we assume this is the position at which tree is present. We undergo optical illusion of changing the path of light ray due to total internal reflection, so that we undergo optical illusion that light would be came from here. So that we assume there is some pool of water. We have observed inverted image of tree. We observe inverted image of tree means we assume this is the pool of water. There is pool of water present inside the sand, so that in that we are observing the inverted image of the tree. This is the way in which we undergo the optical illusion, so that there is some pool of water, and we are observing inverted image of tree, And this is actually there is no water and there is no inverted image. Because of total internal reflection phenomena of light traveling from denser medium to rarer medium, we undergo such an illusion. This illusion forms the mirage. That's what we observe in this case also. Suppose you are observing at the farthest distance on the highway who are actually traveling on the road, and the same phenomena takes place here, and this is known as the mirage, formation of mirage. So students, today we completely concentrated on only one topic, that is total internal reflection. We studied the phenomenon of total internal reflection, and I explained the phenomenon of total internal reflection, and I derived the expression for critical angle, that is sin C is equal to 1 by mu, and consequence of total internal reflection, that is optical fibers. Nowadays we are using optical fibers even as light pipes to see the inside organs of a human body. In medicine they are also very much useful. In communication they are very much useful. And like that, optical fiber and their application, and sparkling of diamond, and reflecting prisms, and mirages, which are consequences of optical fibers discussed in this, especially in this part of our discussion. Thank you for listening. Thank you very much.